not time to be left behind. If you have questions or try to follow up. Okay, the good thing now is that we'll start a new chapter. It's linear algebra, pure linear algebra. Okay, but again, you need to understand the second, I call it second chapter, is the base. Okay, no questions on this? If you want a quick summary, it's just either you formulate the problem as deterministic E square with some prior, or at the end we formulated it as maximum likelihood estimation. It doesn't have a prior, and we make the link from maximum likelihood statistical approach to the least square. Okay, to the weighted least square, where the weight is the inverse of the covariance in a Gaussian setting. Okay, and we linked it to the L1 if the distribution of the noise is exponential. It's better statistical model for outliers. Okay, we're good. Okay, I'll move to now. I'm going to this chapter and the next chapter and the next chapter, chapter after that, how to solve an inverse problem. Okay, we're still in a linear setting. Okay, and you will see in linear setting we know how to solve them, and we have a very nice, efficient tools to solve a linear system. Okay, so why we care about solving a linear system? We're working on linear problem, so it's already linear. It's GM equal D. Okay, and I will split this chapter into two parts. One part where I'm solving AX equal B, where A square and invertible. And the second part is A can be anything, any A. I don't know how you call it. A general matrix. Okay. Why I care about this one? Because in many problems, an inverse problem, we end up solving a square linear system. Like if you take the even determined is directly square invertible. If you take the overdetermined, you're solving for this, right? And why? So basically, instead of solving for this, you can solve for a linear system right? This is a linear square, and if this is invertible, as we're saying in an overdetermined case, so I'm solving a linear system AX equal B, where A is square and invertible. Same thing for this. If I want to solve this, how do I solve it? For the maximum minimum length. This is really square. If I want to solve the minimum length with a linear system, A square and invertible, what do I do? Any guess? Not really, I just solve for the first part here. GTGY equal D, right? I get Y, and then I multiply by GT. If I solve for GT, if I'm not mistaken, right? Then this will give me Y equal GGT minus 1 D, right? Once I get the Y, then the minimum length solution is GTY. right? So again, it comes back to solving a linear system z square where a is invertible. Okay? So in many situations, I come back to solving a x equal b where a is square invertible, and that's why I will start from there. Okay? Then we'll go to the general form. Okay, so let's start from the first part. I'm assuming you did these things already, you know, the how to solve a linear system ax equal b, right? How do you solve it? How do you solve a linear system ax equal b? Gauss elimination? Everyone familiar with that? Okay. Gauss elimination is what you did in, you know, I think even in high school probably. Okay. So Gauss elimination is the standard approach, and I'll skip it. Okay. So basically, Gauss elimination, it has three. I have it in the slides. It has three operations. Multiply by the row by a constant, right? Then plus or minus the row depending on the constant. And your idea is to go from matrix that is AB into a form that is upper triangular, right? B tilde. Okay. Once it's upper triangular, then you start from down and you find the unknowns one by one. Okay. You find the last ones, and you find the one above it, and then all the way up. Correct? So I just summarized it here, but again, it's three. You know, you just take the row, you multiply it by a constant, and then you add it to the to the row above. And the idea to have to go from a x equal b to upper triangular, and you can solve it. Straightforward. Okay? If I remember correctly, it has n cube operations. Yeah, it's in n cube, which is quite expensive. Okay? Do you have questions about this? For a move? This is algorithm, but you know, it's much simpler. It looks complicated, but it's nothing again. Okay? Everyone familiar with that before I move on? Okay. So Gauss, you might hear about Gauss-Jordan. Do you know what's Gauss-Jordan? Gauss-Jordan is, instead of going from AB, you go from A, B, you go from identity. So you start doing operation from the other side. Don't do it. Okay? Because you're just doubling the operations for nothing. Okay? Don't do it. Just do Gauss. Because otherwise you start doing operation from the other side. So 2n cube. No need. So I mean, once I get there, I can easily solve it. Okay? This is Gauss-Jordan, this is Gauss. Okay? So stick with Gauss. Okay, I'll go to something, I'm not sure if you heard about it, is LU decomposition. Anyone? Who heard about it? Yes. So LU decomposition, it's not, you know, LU decomposition is, yeah, one lower triangular, one upper triangular. So basically A equal LU, where L is lower triangular and U is upper triangular. Okay? This actually, why I would, you know, if I have Gauss, why I would care about doing that? Anyone? Actually, this is Gauss, more or less. Just elegant way to do Gauss elimination. Okay? Did anyone hear about this? This is just, I will show you, it's just a very elegant way to do this. But why I would need it? It's more or less the same. Why it's useful to have it? Okay, assuming I have A equal LU, okay? How do you solve AX equal B? take L and I plug it here, A, I get LU X equal B, right? How do I solve this? Of what? I don't think, you know, the whole thing I'm doing it, I don't want to invert. I just want to solve a linear system. Okay? I want to solve AX equal B. The idea here is I want to compute X without inverting for A. That's what we're doing actually. Right? Because inverting means that also I need another matrix to store that is A minus 1 that I don't want. Okay? I'm trying to find A, X. You know. If someone told you solve AX equal B, didn't tell you to invert A, don't invert A. Okay? So how do I solve this? If I have L upper, lower triangular, U upper triangular. L for lower, U for upper. I can solve Ly equal B, right? I take this as Y. Once I find, since this is a lower triangular, it's very easy to do it. It's the opposite of Gauss. Instead of starting from down up, I start from up down. Okay? Once I find Y, what do? I write Ux equal Y, right? And then I have upper triangular, then I do Gauss. From down up. So first up down, then down up. Okay, or tell me. Make sense? Okay. Okay, so if I have this, assuming I have LU decomposition, I can solve this system. Okay, why I would do this instead of doing this? They are more or less the same actually. But why I would do this? The difference between this one and this one is only because here my system depends on me, on B. So basically if I give you another B, you will have to do the whole operations again. Right? If I give you a B prime, you will have to do the decomposition again. Here, it doesn't depend on B. So once I have the LU, I can do it for B, I can do it for B prime, and I avoid the decomposition. We got it? Okay, if you're confident you only need one this for linear system, do Gauss, it's fine. If not, you have to do this. But what is the disadvantage of this compared to this? I have two new matrices to store, L and U. Here I'm not storing anything. I'm starting for A, and at the same time, I'm not storing anything new. I forget A, I get to another system. I'm not storing. Here I need to store L and U, so no free lunch. Okay, if you think you want to need it again, then do this. If not, do this. Okay? Okay, now let's see how we do this. And I do this from here. Okay? This is what I'm going to do, just quickly to show you that any matrix A can be written as LU if its L is invertible. Actually, not completely true. I'll come back to this at the end. I don't want to complicate it from the beginning. So basically, when you do this operation, you take the line, you take this line, this row, Ri, and you replace it by Ri plus lambda ij Rj, or Ri plus 1 if you want. Okay, usually if you want this I plus 1, I plus 1. You understand what I did in here? This is the ith operation in a Gauss elimination. I took the row Ri and I wanted to set 0, the element, you know, because I'm trying to make it upper triangular, right? Okay? Do I need to give you an example, or you're seeing what I'm talking about? Okay, so this operation, I did this operation in Gauss. Okay? I can write it in a matrix form. How do you write this in a matrix form? So basically, assuming you're getting like this, and you have number here. Then you take this one, lambda I plus 1 will be equal to A I, this one divided by, if I'm not missing anything, I'm not thinking much here. Okay? And then when you multiply, the idea is to set this one to 0. So this one minus this one. Okay? So you're just making multiplication and you're setting it to 0. Now, I can do this as in a matrix form. I can write this operation as a matrix form. How do I write it as a matrix form? This operation can be written as a matrix, multiplication by matrix. Yes, it is. It's like multiplying the matrix after operations A tilde, I don't know how you call it. is multiplied by a matrix Mij, which is equal to what? It is ones, 0, and here I have lambda I j minus lambda I j. Depends, if you're taking minus here or not. If you want to get rid of this minus, you can take the minus here. If not, you have to take minus, not plus. Okay, since I took plus here, then I'll take minus here. I'll get rid of the minus. So basically, this operation is just multiplying m by by the matrix Aij, if you want, where Aij came after several operations. Every time I multiply by m. So basically, when I'm doing Gauss elimination, I'm multiplying every time by m12, m13, m14. First I make sure that the first column is number and zeros. Then I go to the next and I take zeros and I make it upper triangular. At the end to get an upper triangle. Pivoting, I didn't get there yet. Okay? You understand what I'm doing? So I start from a matrix A, right? And I start multiplying by m 1, 2. I don't know, but let me get the notation. Or m21 if you want, I don't care about, check it. Then m31. And then, after a while, I'll get to a matrix that is upper triangular. Okay? All this, I'll write it as m. L is equal to what? In this case, the LU decomposition I'm looking for. You have MA equal U. So A is equal M minus 1U. Actually, M minus 1 is L. The lower triangular I'm looking for. No, you will see that I don't. Inverting this is super easy. Good point, but I will show you that you don't need to invert. Okay, but I'm getting to it. Okay, but what I'm saying is that if I take M equal L minus 1 or L equal M minus 1, there are two questions. First, is this lower triangular? Right, because I promised you at the beginning that L is lower triangular. Is it lower triangular? And if so, do I need to invert it? The answer to the question was yes, it is lower triangular, and inverting it is super easy. This is the beauty of it. If you agree with what's there, I will talk about why it's lower triangular, why it's super easy to invert. Okay? So why it's lower triangular? Yeah, but I'm multiplying several m's, right? All the m's, all the operations. M is the multiplications of all the IGs I did to make it upper triangular. But all of them are lower triangular, right? With 1 and 0s. When I multiply them together, M, if you want, is the product of all IJ of MIJs. Okay? You'll find that is equal to what? Very nicely, it is equal to 1, 1, 0, and lambda IJ. Just multiply this by another matrix where it's all 1, but it has only a number that is non-zero. You will see that it's equal to you're just adding a lambda to it. Straightforward. So it gives you a lower triangular matrix. You understand? Do it, by hand. Just take a matrix. Take 1, 1, 1, 0, 0, 0, 0, and 0, 2. I don't know. Multiplied by 1, 1, 1, 0, 0, 0, 1, 0, 0. This will be equal, it's like adding 1 here. Straightforward. So every time you're adding a lambda G on a lambda IJ and the lower triangular. So at the end you get this matrix and it's lower triangular. Okay? So now I showed that M is lower triangular. What about L? We can easily show, that M minus 1 is equal to how do you show that? If you want to show a matrix, the inverse of a matrix is equal to something. How do you show it? Yeah, just multiply this by this and you show that's equal identity. Okay? So there is no inversion. Actually, you're just taking minus m and adding to identity. So you're just multiplying this by minus, and adding identity. So the inverse L is actually equal to what? Because you're taking minus 1 plus 2 identity. So you're adding 1s to the diagonals. Minus 1 plus 2 is equal to minus 1, and the rest is multiplied by a minus lambda. So the inversion, it's true there is an inversion, but it's very, very straightforward. You're just changing the sign of the lambdas. So the inversion is super fast. Okay? All what I did now is, in MATLAB, is you write LU. Okay? And it gives you an LU. There is one subtlety here about pivoting, permitting rows. Okay, this decomposition doesn't always exist. It only exists when, let me see how to say it, the determinant of the leading matrices is non-zero. Okay, let me write it. This decomposition always exists. I can remove this. It's straightforward, You have it in every linear algebra book. Okay, I want you to know where it comes from. Okay? And in MATLAB, use LU. But please just understand where it's coming from. And in terms of, I tried to summarize it here if you want. I'll send you the slides. Sorry, I forgot to send you a slide. So I'm writing it here, okay? In the slides. I tried to summarize it. Don't be confused. It's minus lambda or plus lambda. It depends what how you're defining lambda. IJ. Okay, sorry, sometimes I write plus, sometimes I write minus. Depends how you take. It's minus A or plus. Okay, and I wrote it here. So everything I wrote there is here. And even wrote the algorithm. And the only advantage is to store these matrices LNU. Okay, there is one subtlety at the end, is when this decomposition always exists. If I take a matrix okay, when I talk about leading matrices is this matrix, the first one, matrices I said. This is the first one, this is like a second one, and this is the third one. Every time you take a chunk or you make it bigger. Okay? The determinant of these matrices should be non-zero. All of them. Okay? This is a condition. I will not go to all the details. In my situation, is the determinant of the second leading matrix is non-zero. Which means that this matrix is invertible. Actually, it is. I wanted to write 2, 4. If I write it 2, 4s, then it's not. Okay? Then you cannot do the LU decomposition. You can go around this by doing what? By permitting these two rows, swapping these two rows. Okay? So at the beginning, you can swap to make sure that all the leading matrices permute are determinant non-null. And you can do that. So basically, the general form is not A equal LU, it's PA equal LU, where P is a permutation matrix. for some rows. Now if you write in MATLAB LU, it will give you two matrices, L and U. Okay? But P is already in L, because A equal, if you want, P minus 1 LU. Okay? It will be already in L. If you write L U P equal LUA, it will give you P separately. Be careful. You understand what I said or not? Got lost? Okay, I'll repeat it. This LU decomposition doesn't always exist. If it only exists if the determinant of these leading matrices, every time you take a new column and new row, okay, the determinant of these matrices should be non-zero. So these matrices should be invertible, the leading ones. Where? So this is the original matrix A. I want to decompose it. This is A. I want to see if I can write it as LU or not. I'm saying that A can be written as LU if if this one has 4 columns and 4 rows, then I take 1, 2, 3, and then 4. It has 4 leading matrices. Okay? The determinant of these matrices should be non-zero. Otherwise, I will have a 0 somewhere in the middle. I flip it. I just need to make some permutation to make it work. Okay? When I do a permutation, I can multiply the matrix A by P, permutation matrix. When you flip a row, how to write it as A multiplied by something? If I flip the second and the third, swap. Yeah, but it's like multiplying A by another matrix. What is this matrix? We call it permutation matrix. Anyone? Permutation matrix. We've seen it. Not really? From the good old days? Okay. It's like you're multiplying by 1, 0, 0. It's like the identity, but you're flipping the second and the third rows. So it becomes 0, 0, 1. If I'm not mistaken, 0, 1, 0, 0, 0, 0, 0, 1. You multiply this by A, you get the swapping. You can swap, but it's like you're multiplying the matrix by this. I call this permutation matrix. You see what I mean? When you swap, it's like, this is a swapped matrix, if you want. So if I want to flip these, I should multiply A by this matrix. And if I flip another row, I multiply another matrix. At the end, I will get a P. Yes. You're not changing anything. At the end, I don't care. I want to solve AX equal B, right? As long as I'm getting X. Because when I multiply by P, I multiply by P. Okay, so you flip the data, yes. Okay, I'm after X. But, so at the beginning, yes, indeed, you should swap the B's. So you should multiply by PB at some level. Yes, so if you have the data, you should also flip the data points that correspond to the rows of the A you flipped. You're right, I should have said that. Okay, then I have a system like this, and I'm finding X. Okay, then this one equal LU, and I solve it, but I'm solving for LUX equal PB. Yes, you're right. It's good to visualize it, as you did. Okay, so basically first and then when I get PA, and then I decompose it into LU, and then I'm good. This is the only subtlety I want to talk about. Okay? Again, if you write LUA, it will give you 2 matrices. If you write LUP, it will give you 3. Be careful which one you're taking and for solving with. Okay? But before solving AX equal B, you need P so that you multiply by PB. Right? Otherwise you're solving another problem, I agree. You need to flip the B's. We understand? Okay? This is the only trick you need to be careful about. This is why you need to understand where these come from, because if you write LU and you think MATLAB will give you LU, no, it's giving you PLU. Okay? It's already embedded in L. Okay? Clear? Practice it at home. Just write LU. Write LUP. Okay? We're good? Yes. I'm sorry? Where is that? Bottom right here? Okay. All of them, it becomes triangular. But then you can invert each one if you want, and invert the inversion. And multiply the inversions, then you get the other one. Big M, so it's like taking, because it's inverse, inverse, inverse. Because, so you flip them. Because we said M is equal Mn n minus 1, M multiplied by Mn n minus 2 till M to 1, right? Okay, the inverse of this is M to 1 minus 1, the inverse of each. If you think the inverse of each is correct, then when you multiply them, then it will remain upper lower triangular, right?
Yes, but the value is not directly minus lambda I.
The values, it will be minus lambda ij, as far as I remember. Check it, if not, we can talk about it, but it should be. Okay, write it down, it should be, if I remember, it's not lambda tilde. It should be minus lambda ij.
Yes, the single one is true, but it's like a general.
And when you multiply them together, it's just putting triangularly, all of them, next to each other. It should, because you have one lower triangular multiplied by one lower triangular with just one non-zero element. You're just adding them to each other. Okay, check it and let me know. Otherwise there is a problem somewhere. Okay, now I will go to Cholesky decomposition to finish with this first part. This is LU decomposition. It has 2 over 3 n cube flops. Okay. And one thing you can exploit is A. Cholesky is quite useful also in inverse problems. A is positive definite matrix. Positive, symmetric positive definite matrix. Okay, if A is symmetric definite positive matrix, we can write A equals C, CTC if you want, or CCT, or BBT. We call it this Cholesky decomposition. Did you hear about this? Did you hear about this? Where C is, here it's upper triangular, B is lower triangular. Okay, it's like LU decomposition. The only difference is what? Since it's symmetric, the Q is the transpose of the other one, because it's symmetric. Okay? So the calculations are twice faster. Okay? If it's symmetric, use that. Cholesky, it's faster. Twice faster. And in many cases, when we do inverse of least square, why it's important? Because UTG is symmetric. I wouldn't do LU, I would do Cholesky. When I compute x equal b, okay, I use Cholesky for this. I wouldn't use LU because it's twice faster. Okay? And how Cholesky works? Okay, here I wrote it in the opposite way, okay? Depends how you define C, upper or lower. And LU was 2/3 of n cube, this one is 1/3 n cube. You save twice the calculations. Factor of 2. Okay, if you want to show this, all you need to see is this. Okay, I'm giving you the answer to not spend much time. This is equal to this. You just write it down and multiply 3 matrices. If you multiply this by the transpose of this. So A0, matrix multiplication by blocks. This one multiplied by this one is A. This one by this one is 0. Right? Is A0 plus 0. Matrix by matrix. This one is V over A, and this one is this matrix remains unchanged. Then you can take the transpose of this, and if you multiply these two by this, you will see that you will get this. Okay? if you agree this, what is the algorithm to decompose A into CCT or CTC? If you want to apply an algorithm. So I start from matrix A. And then I write it in this way. These are positive because it's definite, symmetric definite positive. These elements are positive. I can take this IH squared. This is the first element. Okay? And I split it into this way. So it's basically I made the first element here is 1. Then I take this one and I do the same. And I make it 1, 0. At the end I will get identity here. A matrix here that is upper triangular, a lower triangular, and a matrix here that is upper triangular. So the algorithm is straightforward if you agree with this, and it's straightforward. So I get at a point where I have identity and this matrix. Then I take this matrix, I split it into as these. And I do it one by one. And at the end I get identity. Okay, and in MATLAB it is also one command, it's Cholesky, it's Chol. C-H-O-L. But you can write Chol lower or upper if you want, you know. If you see Chol with B is 1 fraction of a second faster than Chol with C. Why? This fraction of the second is the transpose. It does one and it transposes the other. You understand what I mean? Okay. So what I'm trying to say, do you agree with this equality? Huh? Okay. Do you want to show it? Okay, let's multiply. So I have A0 vector V over A and a matrix B. No, A squared VT. This matrix here, I have, because it's symmetric. Okay, if you take A, I can write it at the beginning like this. This number is positive, this is VT, this is V, and a matrix here. So if you want, if I have a matrix, I don't know, 2, 4, 6, 1, 0, I'm putting numbers, you know, randomly. But here I should get 1 and should get 0 and 3. It's symmetric. This is A squared. This is V and this is B. This is VT and this is V. Okay? I can write this as A V over A 0 identity multiplied by, so A for me is 2, so this is square root of 2, right? Okay, and here I'll get, if you want, V is 1, 0, so this is 1 and this is 0 and this is 0 and this is 1. No, this is 0, 0, right? So 1, 1, 0, 0. Am I mistaken somewhere? Over 2. Correct? I'm sorry? Over radical 2. Okay? But I will do it for the general form. I don't need to write it this way. I can. What I'm saying is that this is equal always to this. And to show that, we can multiply, if you multiply this matrix by this matrix, what do you get? I get A, then 0, right? Then V over A, and then B minus VVT over A squared, multiplied by the transpose. The transpose is A, VT over A, 0 identity, right? If I multiply this by this, I better get this. And A by this is A squared, right? Then A0 by VT is VT. Then VA multiplied by this is V. Then this multiplied by this is B. I get what I wanted here. So what I'm saying, any matrix like this, I can split it this way. If you agree, then to decompose as the symmetric definite positive matrix, I assume that I did some operations, because here it allowed me to make the first one 1. Okay, and then I can take this matrix, I decompose it as in here. So every time I add 1, and at the end I add an identity. And the matrices from this side are all lower triangular, and the matrices from this side are upper triangular. This is the algorithm I wrote in here. Okay, so every time I take this matrix here, and I decompose it as before. So then I add another one, then I add another one. At the end, I did all of them. I become identity here, lower triangular, upper triangular, one by one, iteratively. And I took Cholesky. Right, better? Okay. So yeah, basically the first, the AI equal Li, AI, and the multiplications are the Cholesky decomposition. In MATLAB, it's just one command LU. One command is CHOL. B equals CHOL, C equals CHL, lower. If you put lower, it will flip them. And they are the same calculations. You know, do you know how you get to measure how long it takes in MATLAB for a command? Tick tock, take, put the command, tock, it tells you how long it takes. If you add lower, it will take fraction of a second lower, more, because of the transpose. So it's still doing the other one and transposing it. Okay, it's the same. Just be careful what you're getting. Okay, and this is very useful for least square, and when you have a symmetric matrix, it's faster again. Okay, so when you want to solve a problem like this, you want to solve AX equal B. It's as before, A equal CTC X equal B. I solve first for CTY equal B. I get Y. And then I solve for CX equal Y. I get X. Exactly as before. The only difference between LU is that, again, L is the transpose of U, because it's symmetric. Okay, so some tricks in linear algebra that could be useful in calculations. Okay, and it's important to understand where they come from. I didn't go all the details on demonstrating these things, but I want you to understand that if you use a command, there are a lot of libraries, and in MATLAB, again, it's just one small command. Make sure what outputs you will get. Okay, some details you need to know. And when you compare to LU, is almost twice faster. Okay, so what we did for the first part, we started with the Gauss. We said we can write Gauss in a more elegant way as LU. And if it's symmetric, I can even also more elegantly to Cholesky. That makes it twice faster. Okay? So these are useful techniques for solving a linear system with the matrix square, AX equal BA, and invertible. These are good techniques. Okay? I will start with the general system now, AX equal B. Okay? Okay, now I'm taking non-square matrices. It can be any matrix. Okay? In the non-square matrices, we'll talk about three methods. I will talk about row echelon form. I'm assuming you did that first year university. It's exactly as Gauss, but you do it for a matrix that is not square. You're doing Gauss exactly, but at the end you will not get a square matrix. It will be, the same form as before, but it doesn't have a solution because it's not invertible. It's not square. Okay? If I do row echelon form, I'll be able to characterize the type of inverse problem I'm dealing with. That's what I will show today. Okay? I can compute some solution in some situations, but I don't know what kind of solutions I'm getting. So basically, it's good for characterizing the inverse problem. Row echelon form. In MATLAB, it's REF. But it doesn't allow you to solve an inverse problem in the sense that you cannot compute any square. You cannot compute a minimum length solution. You just know what kind of inverse problem you're dealing with. If it has a solution, if it's even determined, you get the solution. If it's underdetermined, it's infinite number of solutions, and you can choose one, but you don't know what you're choosing. Okay, and the overdetermined case, you don't have a solution. But you can characterize what kind of solution you're dealing with. If you care only about knowing if the problem has a solution or not, okay, do it. Okay, QR. Did anyone heard about QR? Okay, QR is another technique, and again, if you do in MATLAB A/X, it will use QR. Okay, QR is more sophisticated than this one. And QR will allow you not to characterize what kind of inverse problem you're dealing with, but on top of that, you'll be able to determine the minimum length solution or the least square solution. So if the problem is overdetermined, you can compute the least square. If it's underdetermined, using QR, it will compute the minimum length solution. Okay? And in principle, it is slower than this, but you're getting a solution. Here, you're not getting a solution. This QR. And then the ultimate one is the singular value decomposition. It will do what this can do, and on top of that, it will allow you to solve an ill-posed problem. Ill-posed problem in the sense, if you remember, if in some situations the inverse problem is ill-posed, I'll come back to this later. If I change the data a little bit, the solution will change, and this we don't like. We don't like sensitivities to noise in the data. SVD will allow me to avoid this problem. Okay, QR cannot, but SVD can allow me in a very powerful way to solve all these problems, but it's of course again no free lunch. No one will get you a free lunch. There's always a reason behind it. It will be quite more expensive to do an SVD decomposition. then QR. Okay, so we'll do one by one. One to characterize, second QR, characterize and compute the solution, and third, the more powerful. If you have enough computing small matrices, use SVD directly. Don't think. It's easier and much more elegant. Okay, but in MATLAB, you know, if you don't care about if ill-posedness is not a problem, QR is faster for calculation. Okay, the beauty of this one also, you will see one solution for all. You don't need to think. You do an SVD decomposition and tell me this is my solution. And if your solution happen to be overdetermined, it will give you the square. If your solution happen to be, if your problem happen to be underdetermined, it will give you the minimum x. The same formula. Much easier to do. QR is more complicated, you will see. But if you code it, if you happen to code it, it will be faster. Okay? Let's do the row echelon form. And row echelon form is very straightforward. It's Gauss elimination to a matrix that is not square. Okay? One by one. Do you know what is a pivot element and a free element? So we're doing row echelon form now, and you're basically you want to solve a x equal b. Now when a is not square, you know that there is no x, right? in general, not all the time. So I'll do a row echelon form to see if there is a solution or not. The row echelon form, I start making it upper triangular, as I did before, and then I look at the end product. So I put a and b, and I want to get it into upper triangular u b. Okay? Just by doing the same operations as I did in Gauss. Now I will define a pivot element. What is a pivot element? Is the first, after I did the transformation from AB to UB tilde, okay, pivot for each row is the first non-zero element of the row. We call it pivot. So here is 3. So if I take a matrix, I don't know, 1, 2, 4, 5, 7, okay? And then I have 0, 1, 3, 2, 2. And then I have 0, 0, 0, minus 1, 1. Okay? Yes. You can, if you want. Does it, you know, you do it as one so that when you solve UB, you have ones, it's easier. You don't need to divide by this number. Otherwise, you just have to divide, but it's the same operations. You're not gaining anything. You don't need to. You could, but you don't need to. Okay? Because this one, I just multiply by minus 1 and I turn it into 1, right? It's one more operation. Okay? If I give you this matrix, where are the pivot elements? Okay, if it's not a pivot element, it's a free element. What is a free element? The 0 is a free element. There is another one. Why we call it free, do you know? Why is it a free element? No one knows? Because I can choose it freely. In the sense, if I want to solve this in linear system, okay? If I want to solve this linear system, this one is determined uniquely. This one is determined uniquely. This one is another determined element. I can choose, I can put any value. I don't care. Because, you know, think about it as this A, X, think about it as U, X equal B tilde. So this one I have this matrix multiplied by x1, x2, x3, x4, x5. Okay? This x3, it can be any value. It's underdetermined. This is an underdetermined problem. Because it's 0 here. It can be anything. It will not change the equation. Yes, I will get there. You're jumping. First understand free elements. This one also is free. Why? Because my first equation, I'm solving from down up, right? From bottom up. My first equation is x minus x4 plus x5 equal 12. This is my first equation. I can set x5 wherever I want. Basically, this equation is telling me you have one free element. I can check x5. Once I get fixed x5, I can compute x4. I go to this equation, right? I have x2 plus the 3x3. These two were determined from down. I need to fix this one where it's 0 to get this one. And then I get this one. So I have 3 elements, pivots elements that I can determine, but I have 2 that are free. Okay? free element if it's not pivot. What do you mean? This one is pivot because it's the first non-zero element. I'm saying look at only the, I'm talking free in terms of as again, which one I can set, which one I can is set by the equations. Which one is I can choose whatever I want. It's free. Okay, link them to again x1, x2, x3, x4, x5. So basically, this is a pivot. This one is the second row, is the first non-zero element. This is 1, 0, 0, 0, and the fourth one is a pivot element. The rest are free. So basically, this one and this one, in the sense that these are free. Okay? This is a pivot column. This is a pivot column. This is a free column. If it has a free element, it becomes a free column. If it has a pivot element, it becomes a pivot column. Just definition. Okay? If you agree with that, I will come to what you were asking before. Now, my first question, when I do the row echelon form, ref, how do I know if the system has a solution or not? Give me quickly, if the system has a solution or not. What do you do? By looking at the row echelon form, you can quickly tell me, Ibrahim, this AX equal B has a solution. Has a solution. I don't care, unique or not. I'm saying it has a solution or it doesn't have a solution. When does it have a solution? No. I'm saying has a solution or doesn't have a solution. I'm not saying unique or not. You can look at the row echelon form right away, tell me, Ibrahim, this has a solution, this doesn't have a solution. If the last, it depends on this column actually. What this column should be in order to have a solution. Actually, not this column, this column. Wait. Yeah, this column. Basically, you can see it right away from here. Just imagine it this way. You made it this way, right? Okay? It depends. So here, if you have 0, right? If this is not 0, then you have 0, x equals number. No solution. If this is 0, then 0 equal to 0, then this system has a solution. It's underdetermined, but it has a solution. We understand? So actually, it all depends on this, not on the other one I said, on this one. If this one is free or not. Basically, if this one is 0, after you have AX equal B, A and B, right? You made it upper triangle. At the end, there will be a column and numbers here, right? Okay. If this is 0 and this is a number, then you have 0 multiplied the last x's equal to a number. You cannot find x's. So there is no solution right away. But if 0 equal to 0, then there is a solution. Okay, so it depends on this column. If this part is 0, then the column is free and there is a solution. If not, no solution. Okay, right away you can know after the decomposition if you have a solution or not. Okay, with that said, I can also know what type of inverse problem I'm dealing with. So the problem is consistent, the last column is free and rank equal rank B prime. So if you know, basically it has a solution if, as we said at the beginning, the first chapter, if rank of R equal of rank of RB prime, this is a solution, right? Remember, when I add the B, it doesn't change the rank, so it has a solution. But who can fill up this, and I will stop here. So what I'm trying to say, which box is even determined, which box is overdetermined, which box is underdetermined, which box is mixed underdetermined. This is what I'm answering your question. How do we know what type of inverse problem we're dealing with? Just by looking at the row echelon form. So basically what I was trying to say here, if this one is a free column, which means this one is 0, then there is a problem. If there is a number, then this one is free and there is a solution. Okay? Now, by looking at the row echelon form, I can determine what type of inverse problem I'm dealing with. Even, overdetermined, underdetermined, mixed underdetermined. It's one of these 4. By looking at that last column and the number of free variables. So the number of free variables is either 0 or non-zero. The last column is either free or pivot. Okay? What I'm saying is that when I combine these two, I can know what type of inverse problem I'm dealing with. This one is very easy to fill up. This case is what? So we're talking about even determined, overdetermined, under, and mixed underdetermined. So you have 4 choices, right? Okay, which one in each box would you put? The first one is the easiest. Okay, if it has a free, the last column is free, it means it has a solution, right? So we just said it. And if the number of free variables is 0, there are no free variables. This means that all of them are set uniquely. Then it's even determined. I'm sorry? The number of free variables, yes, in x, again in x's, because the last column is a b. It's x plus 1, n plus 1. Okay, this is even determined, straightforward. This is the easiest. What about this one? The last one is pivot, so it's not free. No solution. You have 0 equal to a number. If the last column is pivot here, so this area here there is a solution, this area there is no solution. We agree? Okay, if I'm here, the first one we said it's even determined. This one will be what? No? Under, why? It has a solution and it's not unique. It has infinite number of solutions. So this is, actually it's easy if you don't even need to think, because in this case this one will be over and this one will be mixed. But why is this over? This one has a mix, this one has no solution, and some variables are free. This one here. It has no solution, but some variables I can fix them as the way I want. This is a mixed. And the last one by elimination if you want. Okay, there is a part that I cannot fit, forget it, and there is a part I can uniquely determine. This is the overdetermined. A part of the data I'm saying. Overdetermined means that at the end, I get 0 here equal to a number, and then this should be upper triangular. I should not have free elements. All these elements are non-zero. When I'm talking about overdetermined, here should be 0, right? So it's pivot column. This one is a pivot column. This number is non-zero. Then there is no solution. But what this system is telling me, if it is like this, how I'm writing it, then here it can be numbers. Okay, then I can have zeros here. Okay, what's this? This is telling me this is an overdetermined case, and all these are non-zero. Okay, if all these are non-zero, what it's telling me that these axes here, the last axes, okay, do not have, they cannot fit the data. But these I can determine them uniquely. You know what I mean? So the rational form is transforming the data into new data. Part I can fit, part forget it. I'm not saying this is a least square solution, but you get a solution. You understand what I said, or you see what I mean? Now, if part of these elements are 0, then some of them can be mixed. Then I get to the mixed underdetermined. Okay? In the other one, in the underdetermined case, it should be something like this. It should be 0, 0, 0, 0. So these and some zeros here can be free. I can choose them. So the number of free elements is non-zero, and it has a solution. Okay, so it's this. So rational form gives me a way to determine what type of inverse problem I'm dealing with. I can solve it if it has a solution. If indeterminate, I can find the solution. It's one solution. Underdetermined is infinite. Okay, overdetermined, no solution, and that's it. Okay, just by looking at the number of free elements and looking at the last column if it's pivot or not. Okay, this is free, and if it's this way and with a number here, not 0, then it's pivot, and then no solution right away. Okay, so this is what I was saying at the beginning. It allows me to characterize the solution. It doesn't tell me what kind of solution I'm dealing with. What I will do on today's one. Okay, on next Sunday we'll do QR. Okay, and hopefully some of SVD. Hopefully. Okay. I'm sorry. Raw echelon form. It's Gauss elimination. Just Gauss elimination. Okay, but it's not square. So you just try to make it as much as possible as upper triangular, and you look at the rest. Okay, characterize. And if you want to have to know a solution, also you can rule from the beginning rank of A. If A x equal B, this which means that rank of A will be. Okay, it has a solution if this is true. Okay, so now you know how to characterize an inverse problem just by doing row echelon form. On Sunday I will do QR, and you see QR is more powerful. It will give me it will allow me to compute the least square and the minimum length solution, and the least square minimum length solution for mixed and determined forms. Okay, so now we're starting, from next session we're starting going to the interesting part. We're good. So look at it today. It was part reminder and part a little bit new. Okay, QR will be new. Yes, sure, please. If I don't, just shoot me anyway. Don't hesitate. If someone did the linear algebra course in applied mathematics, then they do that. Okay, part of the course. QR, LU, and SVD. Okay? Computational linear algebra. If you care about this, it's a good course. It's useful. If you care about linear algebra and computations. Okay? Okay. If you have no questions, feel free, and we will continue next Sunday, next week. I'm sorry?